Good morning, everybody. Thanks again, Mark, Gilad, all of you inviting me here. I was here in 2019, and then after that, I think we went virtual. So it's again a pleasure to be back. So today, what I'll be mostly presenting about how do you design scalable middleware, and especially on the heterogeneous systems we are encountering, and also taking into account of the HPC, AI, and also data science. As most of you know, we are in a very exciting phase. This year, actually, we got the exaflop system. So especially in the HPC community, people are very excited to really move forward. People have been talking about this for some time, but finally the machine came this year. But now if you go internally, you will see all these machines are being designed with some commodity components. It could be multi-core, many-core, high-performance interconnects like InfiniBand, Slingshot, or it could be accelerators or some kind of storage. So then obviously to this mix, both the CPU and GPU, now we have these new kinds of devices, the DPU, IPU, XPU in general are coming. And also we discussed about, like yesterday, about cloud and all. So if you take a very broad look, all these commodity systems are coming up. How do you design really middleware for these systems which will deliver high performance and also scalability? So that is the kind of the challenge which I'll be talking here. Now, while we are trying to also develop the middleware, you will see the community has now expanded. It's no longer just the HPC. People have been trying to, in a given like a workflow, you want to do HPC followed by some machine learning, deep learning, or big data, data science. So everything is being combined. So then I call it like a convergence. So we need to design something which is like a converged software, which will run on-premise as well as in the cloud, and can also try to satisfy all these different workloads. So this is where in my group, we have now taken an approach saying, can we build all these things on top of MPI library? Okay. Let's say over the years, there are so many different networks. So now let's say I take an example of a Spark. I need to optimize on InfiniBand, or I need to optimize on Slingshot. Instead of like doing per network, as many of you know, as soon as some new network comes, MPI libraries are available. People work on and then put it into MPI. And MPI typically has a very low overhead. So almost like you can run experiments or your applications with almost bare metal performance. So the question is, can the other middleware be built on top of MPI? And that's what I'll try to show you. And that's what we have been working in my group for the last several years. So I'll start with the MPI library project. I'm sure some of you are familiar with that. Then I'll go into high DL project, high performance deep learning. So there I'll also go into deep learning, machine learning, and also how to utilize the DPUs for deep learning. And then I'll move into this high BD, we call it high performance big data project. So I'll try to again show how Spark ecosystem can run on top of MPI. Similarly, how Dask can run over MPI, and we get great performance with this kind of portability. I'll talk a little bit about commercial support also. Like over the last 5 years, we have received a lot of requests from all these organizations who are using our MVAPIs and all other middleware to really provide commercial support. So we have actually now a commercial spin-off providing that support. And then towards the end, I'll talk a very little about that AI Institute. I think I talked to Mark yesterday. We have been recently awarded a $20 million grant. I'll talk more about that at the University of Leicester. I think this is 1 o'clock. I'll go into more details, but here I'll talk a little bit about that, and that's how I'll conclude. So just to give you a perspective, how many of you have heard of the MVAPIs project? Okay, quite a few. That's very nice. So we started almost this project almost 20 years back, day one of InfiniBand. When InfiniBand was introduced in October 20th, 2000, there was no MPI library. Nobody knew how to utilize that InfiniBand. So at that time, I approached Mellanox people to give me hardware just for like 2 or 3 nodes. And then we had the first MPI running over InfiniBand, and it was demonstrated at Supercomputing O2 almost 20 years back. But since then, I'm very proud of my team. We have been working on this project now for 21 years. So currently, not only we started with InfiniBand, but we have extended it to all the different networks. You name any HPC network, now we have the support. And not only that, we have grown over with also MPI standard. Now we support all the MPI 3, MPI 4. So here you will see like almost more than 3,000 organizations in 90 countries are using these libraries. And we, just from our website, we crossed like a 1.6 million downloads. Okay, so every day we get thousands of these downloads, and of course these don't take into account like our stacks are available with Red Hat, SUSE, SPAC, OpenHPC. We don't keep track of these. These are the direct counts from our websites, and also it enables a lot of these top 500 systems. So we have been there in this field. So just to give you a perspective, like how people have been downloading our stacks over the last several years. But this is like the heart of the system. So what we have done is this is like the MFP2 architecture. We take care of like left-hand side, if you see all the different networking technology, their features, and then the right-hand side is all the processors, the CPU, GPU, DPU, and their features. Okay, so I call it like a supply-demand side. So if a new networking technology comes, it typically has some features, and this is where, being in academia, we are very interested. My students and I are interested, saying how do you take those features into account and come up with the better designs for MPI or big data or any of this middleware, and then we publish those, and then we take actually into really convert into production quality software. In my lab, we have almost 200 servers which continuously do QA testing. We have developed in-house testing over the last 20 years. So, and then once we publish the paper, in 6 to 9 months, we really push it into our production quality software so that people can really take advantage of that. So here I'll just try to give you a little bit of sample numbers just to give you a feel. Like let's say if you take like the latest MFP, this is our public release, 2.3 series. That is a stable release. We have been enhancing. We did it in the March. That time we supported like a Rockport network, a Craze Slingshot 10 and all. And recently, in August, we have this new 3.0 series have started, and this actually has support now for UCX, libfabrics, all the 2 different major initiatives which are taking place, and also we have support for a Craze Slingshot 11. So that is the network which is being used on the frontier, the #1 system in the world. So now you can actually utilize our stack for all these different interconnects and systems. So just to give you a feel, I mean, we really try to optimize. I mean, MFP's project has been very synonymous with performance. Okay, so here if you take a look at this, like the very latest AMD Milan system, the servers with SDR 200, that is the InfiniBand 200. You take a look at like this is the internode latency here. You will see, I don't know, 1.8 microseconds, node to node we deliver, and then within the node, if you see here, like a core to core, we give around 190 nanoseconds MPI latency. Core to core within a socket. So we are now actually MPI library we are designing at a nanoseconds level. Okay, so it really, even if you like those of you know the software engineering, I mean if you even put the if then else while, I mean unless you take care of those loops, you will lose time. So we go to that in that level and then try to make sure that we are trying to really run at the bare metal performance. So that is like point to point. But as you know, MPI, those of you are familiar, has a lot of operations, okay? And the most challenging ones are the collectives. Okay, these are like the broadcast, all reduce. As the system sizes have been scaling, this is where continuous optimizations are needed. Okay, otherwise a lot of applications use those operations, and if you don't implement those properly, you lose. Okay, so these are like a blocking collectives. So we have this, we have done a tight integration with InfiniBand SARP, that is like in-network computing. So now you can see these are the numbers taken from TAC, Texas Advanced Computing Center, that has the largest InfiniBand deployment. So these results are from 8,000 nodes, okay, the full scale system. And then you can see here like we have an MFP2X, which is an advanced version. Now if you do a very tight integration with a SARP, we can like this is the MPI barrier, we can give you a factor of 9, reduce, everything we can try to optimize. And if we can optimize those collectives, the applications running on top of these can actually try to see the benefit. But those are the blocking collectives. But recently, there's a lot of actions happening with the non-blocking collectives. How many of you know the non-blocking collectives? Okay, some of you, that's good. So the simple idea is that think of like a blocking collectives. That means if I'm doing all-to-all, while all-to-all is taking place, nobody is making progress. Like all the computations, they are helping with the non-blocking, the blocking collectives, but they are not doing any computation. Okay, so pictorially here you will see, I have the computation, but now if I change that to non-blocking, while the operations are going on behind the communication, my computation can also proceed. Okay, is a very simple example I give, like, on a Friday evening, you have your friend, you decide to go for a movie, and your friend says, yeah, I'm coming. But you just don't sit idle, okay, on your driveway waiting for your friend, unless you don't have anything to do, right? But we have a lot of things to do all the time, so we say, yeah, we'll continue to work. You come and then we'll go to the movie, okay? So that's the kind of the paradigm we are trying to take it here. So while the computation is running, communication takes behind the scene, and then I can actually have overlap of computation and communication, okay? But the biggest challenge is, how do I know that this communication, who will make the progress? Because many of these communication, you need to send me a message, I need to combine it with another message, I need to send it out. And I'll show you later on the DPU. DPU technology comes the very best in this kind of scenarios. So we have been like continuously focusing on these non-blocking collective optimizations, and there are two degrees here. One is to reduce the latency, and the other one is to exploit the overlap, okay? Because I want to provide the overlap of computation and communication. So here if you see, this is an I barrier. So let's say think of like this is our MAP is to 236, and then 237, we reduce the latency by almost factor 4, but at the same time improve the overlap, okay? So that means that at the application level, you can actually, instead of doing blocking collectives, you can do non-blocking collectives, initiate, and then continue with the computation, okay? So those are like, I'll come back to the DPU in a few more slides, and you will see, in fact, that will get very much glorified, the need. But here it is some example of Slingshot 10. That was like the earlier generation of the Cray Slingshot. So it just shows how we perform compared to the other MPI libraries. The very latest, the Slingshot 11, this is running on the frontier. If you see here, we get around, this is the new release which we made just 2 months back. So around 2 microseconds. It's not as good as InfiniBand, but these are the first cut, whatever is available there, and I'm sure Cray is optimizing their stack, and then we'll see how much it can be improved, but we get around like a 2 microsecond latency here, and bandwidth we saturate almost to the peak, like a 24 gigabytes per second and 42 gigabytes per second. So this is the CPU side, but let me start with the GPUs, okay? The GPU has been there for many years. In fact, this work we started almost 10 years back. And thanks to Paul, I think all these work were done on your system. How many of you heard of a term called GPU aware or CUDA aware MPI? Okay, some of you. So actually we started that. So this was a 2011 paper from my group called GPU Direct. RDMA was just coming up. So the idea is that if you have a GPU environment like this, GPU and InfiniBand, most of the time people do, like let's say you launch a kernel, and after computation is over, when you want to send the data to the outside, you do a CUDA mem copy, MPI send, MPI receive, and then another CUDA mem copy. So the data goes through multiple steps, and especially if you have very large data, latency becomes very high. So this is where at that time, 2011, Mellanox and NVIDIA worked on the GPU Direct RDMA. So we were a part of that, and Paul's group, Filippo, he was there at that time. So we tried to really, this was a Wilks 1 system, so you people provided the test bed, and we really realized this, the CUDA aware MPI. What we proposed here is that instead of going through all those steps, you just do on the sender side, you just call MPI send device buffer. Just like you call from a host buffer, you just call device buffer. And on the receive side, you just call saying MPI receive on this device buffer, receive buffer. And everything else, the MPI library will take care. You don't have to worry. The users don't have to write all this CUDA programming for communication now. Of course, computation you have to write, but communication will take care, and that leads to really high performance and high productivity. Okay? And 2011, we actually showed 1.18 microsecond. I remember the latency from GPU to GPU in 2 nodes. Okay? InfiniBand was delivering around 1 microsecond latency. In another 180 nanosecond, we were able to achieve the communication. And during the last 11 years, almost all the middleware, all MPIs, even the Nickel library, everybody has moved to that paradigm. So now you go and look at any middleware, you will see this CUDA aware MPIs there. But now we have moved to the next level. I'll introduce this called on-the-fly compression. Okay? So if you think of like these days GPU, like take like a A100 or even V100, there's so many computing cores. Of course, it will help accelerate the computation, but when you are trying to do communication, these cores are idle. Okay? And especially this modern workload, if you see AI and all, we are sending big messages. So the idea is that can we do on-the-fly compression before sending it? Okay, because these cores are sitting idle during the communication. We don't want to take the cycles from the computation. But communication, before I send a 4 gigabyte message, can I compress using the cores, and on the other side I'll decompress? Okay, of course there will be overhead, but no, the message size also can be reduced. So then if I can do the design properly, I can actually win over. And that's what we have shown this. This was a best paper finalist at IPDPS last year. And here we are trying to show the end results, like this is a AWP ODC, which is like a earthquake simulation. And at an application level, we are able to show here in this case, flops. So higher is better. We are able to deliver like at an application level, 18%, 35% benefits. Okay, even though we have these overheads both sides, but the message size is reduced. Okay, and then on the right hand side also similarly we are seeing the reduction in the latency. And so then recently just ISC this year we extended that. That was like a point-to-point compression. But now you can take that idea to all the collectives. We are trying to optimize each and every collective. So this was an all-to-all compression PSDNS. It's a fluid dynamics code. Similarly, we improved by 29%. This is actually a deep speed, which is a deep learning code using frameworks. Similarly, kind of a 35.8 performance benefits. And these are all available in our latest MHAPIS2 GDR. So if you have a GPU cluster, you can actually download this, and you should be able to see these kind of benefits. Similarly, we have done like those if you're familiar, there is a all-to-all V. Those are the very complex operations. Okay, so there also we have used this on-the-fly compression, and this is the library which is being designed at Oak Ridge National Lab with Tennessee, HEPT. These are new FFT libraries are coming, and these are the kind of results at that HEPT level. You see almost like a factor of 28, factor of 5. We have been able to improve that. Okay, so if we can improve this kind of libraries, then it has a big impact on the. This with a compression. Okay, so these are the very latest compression, and then we have also optimized the algorithm also a little bit. Okay.
Is that particular router will be very heavily dominates the commonly used UK code for electromagnetic forecasting?
Okay, sure.
With a lot of Cambridge, so that's really
Sure. So this is again all the optimizations are available in the latest version. So if you have those users, they can take advantage of it.
It's going to be dominated by FFTs.
Yes.
So that's actually really interesting.
Yeah. So similarly, like so I showed a lot of NVIDIA GPU results, but we also have AMD support. So it is integrated. So if you have AMD GPUs, those are coming together. You should be able to also take advantage of that. And here I am showing some initial numbers here. But let me spend a little bit of time on the DPU. How many of you have heard of DPU technologies? Okay. So the DPU, if you think at a very high level, I call it like an executive and secretary. You can understand very well. So think of like this is the Bluefield DPU. So we have a set of host processors in addition to the RDMA engines and all which InfiniBand provided. Now we have a set of ARM cores. Okay, so think of like those are your assistants or those are your secretaries for a set of executives. So just like in the real world, things can be offloaded to assistants for setting up things, sending mails and all those things. Can we do that within MPI layer or even within an application? So I'll show you two examples. So here we have taken that non-blocking collectives. You remember I talked about earlier? That kind of like if I want to do all-to-all, I want to do bcast, everything in a non-blocking manner, can I offload those to the DPUs? Okay, and this is a MHAPIS2 DPU. We have a library. In fact, this is being done by this commercial spin-off. I'll talk about this Xscale solution, which is also a sponsor of this this conference. So here we have some initial designs like a MPI, I-all-to-all, iGather, iBcast. Let's look at some of the numbers. So you remember the bigger thing is the overlap of computation with communication. So in a typical MPI library, those of you are familiar, typically there are two protocols. One is the eager protocol for short messages, you copy and then send. So you get some overlap. But the larger messages, wherever there is a rendezvous protocol, that means I first need to send you an RTS, you send me a CTS, overlap is very hard to achieve. But that kind of operation now I can offload to DPU. And then you will see your overlap goes up because I am not exchanging. It's just like an executive, you know. You have to set up a Zoom call. You tell your assistants, go ahead and set it up. While those calls are taking place, you are continue to work. Okay, so that is the kind of the paradigm we have brought. So now you can see this is the I-all-to-all, non-blocking collectives. This is a 512 process run, this is a 1000 process run. See, at an I-all-to-all level, the red one is MFAPIS2, which didn't have overlap, but the MFAPIS2 DPU, now we are trying to exploit that overlap. So this is showing when you have computation plus communication, how much time does it take? So here we are able to reduce like by 22%, 20%, 17% kind of things. And then if you take it up, this is a P3DF50, is a very common kernel. And at that level, here again, we are able to give for different grid sizes and all, we are able to give you 18%, 14%, 21% benefit. Okay, so this is on the x86 with DPU. In fact, Paul just gave us access a few months back on the AMD with Bluefield. So we have some numbers and all. I'll share those with you tomorrow. We are doing a collaborative project with Paul. So just to summarize this part, I mean, this MFAPIS, as you saw, I just gave some highlight. I mean, MPI has so many functions. We have been continuously improving it. These are some testaments from Oak Ridge National Lab. Comparing all these are the numbers from Summit system, which is the number 4 now. It used to be number 1 earlier. You can see across different MPI libraries, MFAPIS performs good. And we have been working with this Idaho National Lab. They have actually a lot of simulations on nuclear energy. So they use all these MOVES framework, PETC. So we've been working with really their applications people. And this is very nice thing. We have an annual MFAPIS user group conference. I'll talk a little about that. So last year, this might be common across a lot of HPE center. These days, you know, all different MPI libraries are there, MFAPIS2, Intel MPI, Open MPI, there are a lot of them. People were using all the different MPI libraries, but beginning of 2022, see, all the users moved to MFAPIS2, okay? Because we have been optimizing their code so well. So all the users moved to using our library, okay? Because everybody wants the best performance and scalability on their system. So this is the kind of thing what we have been doing with a lot of these national labs. And this is my best project. Many of you must have heard of this NASA DARTS mission 2 weeks back, planetary defense. I'm very proud. I mean, MFAPIS2 actually played a role here. We have been working with Lawrence Livermore National Lab since 2016. They are actually running all these simulations. Okay, so this NASA aircraft, when it was launched, they have the actual simulation running, the Livermore, trying to match exactly what they are projecting there, and the simulation is also telling that this is the direction you will go, this is how you will hit. And MFAPIS2 actually enabled that. So there was a lot of press releases just happened just 2 weeks back with this. So this is just a summary of the MPI side. So let me move into a little bit how that convergent software stack we are trying to achieve. So if you take a look at, let's say, deep learning, if some of you would have used, I'm sure a lot of you might be using TensorFlow, PyTorch, MXNet and all. How many of you have heard of like a Horobot, Torch distributed, deep speed, etc.? Some of you. So these are actually you can think of like a middleware. Okay. So what we have done, we have actually linked our MPI library to there. Okay. So that means, let's say you are running TensorFlow, PyTorch in a transparent manner, you can actually take advantage of our MPI library. Because MPI library is providing scale out, scale up over CPU and GPU. So we can push that performance to even to the TensorFlow layer, PyTorch layer. You don't have to change anything. It will just run. And this is what we call, this is a project called High Performance Deep Learning. You can actually download, we have a very nice user guide. You download your MPI, you download all these stacks, put them together, and then you are able to get some good performance. So I'll just try to show some sample numbers here. We have been working with some digital pathologists. And this pathologist, as you know, I mean, is a really very driving example of deep learning. I mean, every time, you know, many times we go to the hospitals, they try to take our blood or something and then say we'll run pathology, simple things to more complex like cancer and all. Now, every hospital has so many images. And this pathologist, sometimes they take like 15 minutes, 30 minutes to analyze a slide. And of course, pathologists are very expensive. Okay. Now the question is, can we actually train them with a lot of the images which are available in the hospital, so that we are not telling the machine to identify do the diagnosis, but at least they can narrow down. So if the pathologist is looking at your pathology image, the machine can tell, yeah, it could be probability of like these kind of 5 diseases are higher. Okay? So instead of then pathologist spending 30 minutes, can spend 5 minutes only. And it significantly reduces the healthcare cost. And especially in US, if some of you know, the healthcare cost has been going like a crazy manner. So this is one way to reduce it. So we worked with the pathologists. So in the beginning, they were trying to do, and the biggest challenge is that these are called out of core. These images are so large, like 100,000 pixels, they cannot even fit into a single GPU memory. So this is where you need to bring model parallelism. The data parallelism will not work. So we worked with them in the beginning. They were using only like a 1 GPU. It was taking 30 hours to do 1 pass of training. They were not very happy. We worked with 2 students around 3 months. We reduced to 24 minutes. Okay? So almost we gave like a factor of 15x reduction in time, and now they are able to really jump into more complex model, improving accuracy and all those things. I mean, you just half an hour is like you go for a coffee break and come back. Your training is done, right? Instead of waiting for 2 days. So then recently with the DPU, earlier I showed you the DPU offload for communication. Now let me show you something. You can also offload task or computation. Okay? Of course, the DPU ARM cores are not very powerful, so you cannot really run a full scale thing. So here what we did is like in the deep learning, if some of you know, like we have a data aggregation, training, model validations, etc. So we try to do a lot of analysis, and we saw that you can do the training on CPU, data augmentation on DPU, testing process on DPU. Okay? So it's like a task parallelism. So you can decide based on the ARM core speed which components can run in an overlapped manner. And I'll show you, and this actually was presented at Hot Interconnect last year. And this also, we have an xScale AI DPU package from this commercial spin-off I indicated earlier. So if you take a look at some of the numbers, with the current generation DPU, not even the DPU, the Bluefield DPU, 200 gigabits have come, Bluefield 3, this is just the Bluefield 1. So here you can see, we are able to give you like almost like here up to 17% benefit, the same hardware. Okay? It's not a big factor, but still we are able to offload some tasks to the DPU. With the next generation technology, we should be able to even get better performance. Here it is like a 17%, 13% for all the different kind of the models. So then let me move into the big data side. So the big data, I think if some of you are familiar, this project has been going on since 2013. So in the big data analytics side, you know, the Hadoop, Spark, Kafka, HBase, all these softwares there. So we put a lot of effort there to directly redesign those into InfiniBand verse level. It was very time consuming, okay? I mean, but we had a lot of ideas from our MPI design, so we moved it to the big data. But then what is happening, it is very time consuming. This project is still continuing, a lot of people have been using. So now we have changed the direction a little bit, and that's what I'll talk. So this is like a, let's say, RDMA Spark, okay, which is available publicly, people have been using. So think of like the yellow one is like called IP over IB. It's the same InfiniBand network. You can run Apache Spark, which doesn't provide a native design. You can run that. But the red one is the RDMA designs. Okay, so you can see like a 37% benefit, 47%. But now with the changing the network, let's say Slingshot has come. So now if I want to take the design, I need to totally redesign that for Slingshot, or let's say kernel-less network, any network. So instead of that, now this is where we are trying to bring that MPI layer. Okay, so what we did recently is, if you took a look at the Spark, there is a NAT layer here. And we actually put that into our MPI, on top of MPI, because MPI already has the communication. Of course, there's some semantics mismatch, so that is the challenge we solved. But now if you see, this is an MPI for Spark. These are like some numbers. Let's say this is compared to the vanilla Spark Apache, we can give you almost 3.65x improvement. Even compared to our RDMA Spark, we can give also 1.88x. Because that RDMA Spark code was a little bit older. The very latest MPI has all the optimizations. So it's like a performance portability with very little overhead. That is our goal. Okay? So as soon as a new network comes, MPI library will be available in 2-3 months. Now you can have your Spark running on top of it. You don't have to reinvent or spend another 1 year trying to optimize the stack. Similarly, these are the results, like with the InfiniBand STR200, similar kind of benefits we see. This has not been released. We'll be making a release soon. But we presented this as a IEEE cluster paper. So that's how we are able to really bring all these middleware into a converged environment. And then the new thing which is coming up is the Dask. How many of you are using Dask for data science? Of course, Paul's lab is using. So this is where we have introduced MPI for Dask. Okay. So we have a release already, but now there is a new release coming, and I think yesterday we heard about the SCA project, right? So SCA project is using Dask. Here again, we are collaborating with Paul's group. These are numbers actually from your system, Wilkes 3 system. We just ran last few days. So now you can see for running the Dask, there are two different options. One, you just run over TCP/IP, okay? Or there is a stack UCX, which is the consortium NVIDIA and others are doing. But this is our new design, which is over MPI. As you can see, we can give you almost like 5x faster or 27x faster compared to TCP. And this is running over like a 32 DAS worker, 32A100 GPU. We have a CPU version as well as GPU versions. So similarly, like this is a matrix dot, similar kind of things we can give. So these are actually the Dasks. So now we'll be making this release coming up soon to be released, and you should be able to utilize for all your data science applications.
This work has been done within the Scalable project that we're involved.
Yes.
So we will be demonstrating this functionality, publishing this to the UK community through the Scalable project.
Okay.
We're going through all of these things you're talking about.
Sure.
Rather than one of our clusters and then disseminate the advantages through the Scalable community. So it's very relevant to this meeting.
Yeah, so I mean, if it is being used in the Scalable project, all of you can utilize this. Once we make the release, you should be able to utilize this. So let me just wind down here. And as I said, these are all from the Ohio State University side. We have all these things available, open source, people have been doing, but over the last decade, we got a lot of requests from all the different HPC centers, companies saying, okay, can you give us a really commercial support? You know, there is a 1-800 number. If some issue comes, I cannot do that from OSU side, okay, being a university. But then we found this company, which is called Xscale Solutions. And through that, actually, we have been working. Like our largest customer is Lawrence Livermore National Lab. Their entire, all the machines, all their MPI, we take care of that. Okay, that's how that DART project and all, you see, really signed up kind of things. So through this, now what we are trying to do, not only we provide commercial support, but we provide a value-added products. That's what communities have been looking for. So this is where we have an Xscale HPC, Xscale AI. I talked about this MBAPIS to DPU. So these are on top of whatever OSU things are available. Of course, these are commercial products. We have been using a lot of DOE has funding called SBIR projects. So through those projects, we have been able to leverage funding to develop this. But before I conclude, let me just talk a little bit here. This is the new institute. I indicated this is a $20 million. We got it from NSF. NSF funded some of these AI institutes so far. There are 11 of these. And the broad objective here is to really look forward, like next 10 to 15 years, think of how the cyber infrastructure needs to be redesigned. Okay. Now, of course, in this community, we are talking about HPC, big data, machine learning, but the data is almost always there at some place. But now if you take a look at data is coming from sensors, data is coming from a farmer, data could be coming from all different devices, from a drone and all those things. How do I design the stack for that intelligent computing continuum? Okay, so take a look at like 2035, 2040. So this is where this funding is there. So there is a very short video. I may take 4 more minutes. Let's see. It will give an overview here. Can we turn on the video? Sorry, audio.
While food distributors and public health officials are concerned with how supply chain disruptions will affect deliveries of nutritious foods to communities, current technology can provide data and models to tackle grand challenges such as biodiversity, conservation, and agricultural and food system resilience. But it still lacks the infrastructure to link across data and models seamlessly to answer complex questions from diverse stakeholders' perspectives. Even AI experts are challenged to create standardized solutions across domains because a standardized cyber infrastructure integration with AI just doesn't exist. Enter Icicle, intelligent cyber infrastructure with computational learning in the environment. Icicle is an institute dedicated to building a national AI-driven computational infrastructure that functions as a utility, much like our electricity, water, and transportation infrastructure. This new utility will enable the delivery of AI to end users with the flick of a switch, enlightening solutions for imminent problems of national, regional, and local importance. Icicle will provide an operational rationale and framework for a cyber infrastructure that delivers wide and easy access to smart computing, plus a conversational interface that allows stakeholders from diverse domains to ask questions and receive answers informed by currently available data and knowledge. For example, food distributors, emergency food agency managers, and logistics company executives might ask, which food supply chains will likely be affected by an approaching storm? The Icicle conversation agent might respond with, I will predict future states of your regional supply chain under forecasted weather scenarios and evaluate alternative scenarios. Okay? Upon confirmation, Icicle would then retrieve satellite data on weather, connect to weather forecast models, acquire inventory data for food producers, processors, distributors, transportation networks, wholesalers, and retailers throughout the region. Use AI models to forecast supply chain conditions from a baseline and alternative logistics that maintain consistent food supply for vulnerable populations, and estimate supply chain disruptions based on historical and current data from other locations, mindful of privacy. Icicle will go even further by accessing high-performance computing centers to backcast and learn how reconfigured landscape-scale precision agricultural production and distribution systems could integrate with alternative supply chain infrastructure to avoid similar future disruptions. Using an orchestra of smart cyber infrastructure elements, Icicle produces a symphonic answer that improves outcomes for diverse stakeholders. Icicle holds the potential to transform today's AI landscape from a series of fragmented tools for use by a few to one where democratized AI and integrated plug-and-play architecture empower diverse end users with knowledge and data flows that are science-based, traceable, transparent, reusable, and trustworthy. Introducing AI for CI for AI. AI for everyone.
So this is just a very high-level overview. In fact, today I'll be giving a talk at the University of Leicester. Professor Anjum is the host at 1 o'clock. So there I'll go into very more details of that thing. So this is a very, I am the overall PI, but there are 15 universities, 50 PIs, 60 students, so 110 members are working on this. And you talk about anything, starting from knowledge graphs to model commons, data commons, conversational AI, CI for AI. So everything is there. We have dedicated people, groups working on those. And the broad idea is really looking forward, like 15 years down the road, 20 years down the road, just like the example you saw, like let's say electricity. I mean, these days everybody expect, I mean, you just travel, you have your adapter, it runs. Okay, so same thing can we provide for AI. So that is the whole idea of plug and play design and democratizing AI. So we have actually domain scientists of digital agriculture. We have really people are working with farmers, people are working with food distributions, people from PIs from food and agriculture departments of different universities, milk distribution, meat distribution. So we are really working with all these end people to really take our computer science things to them and then bring their challenges to us. So that's what we are doing. So with this, let me conclude here. Just at a high level, what I showed, like this holistic design we need into account, like HPC, big data, machine learning, data science, everything in that computing continuum. I provided some of these overview, opportunities, and kind of solutions. And of course, now since the example of systems have come, I mean, people have started talking about Jetta scale, right? So we need to aim for those. This is my self-advertisement I'm doing. A lot of our big data work actually has been just published by MIT Press. This is a new book. It will be getting launched. It was released in August. You'll see some special launching event at Supercomputing 22. If some of you are there, please feel free to stop by. And it is available now with Amazon and all the different vendors. I also want to indicate this. We do a annual MIPH user group conference, as I was telling, every August. So we really bring a lot of people who are using MIPH library to share their experience, good, bad, ugly kind of things. And in future, if you'd like to present there, I'd like to invite you. And then, but last but not least, these are all my thanks to all the funding organizations. Otherwise, you cannot do this kind of research. But these are all my heroes. As you can see, like what I presented is like a 25 years of work. A lot of these students have come, they have graduated. If some of these names you will see, they are at all top companies, national labs and all, working. While saying that, I'm also looking forward to a lot of new people. So this is where I think some of the collaborations can continue. If some of you would really like to come to my group and all work, so that your name I can add to the previous list. Okay. With this, I'll stop here, and I believe, Mark, you indicated like we have already started working with Paul. So like this, if there are any other institutions would like to collaborate, we'll be very happy to not only our MPI, Big Data, Machine Learning, but also the new Icicle Institute kind of things. So let me stop here. I know I took a little bit more time. If there are any questions, I'll be happy to answer.